Okay, hi everyone. In this video, we will see how array, strings, and how any information stored in the memory. This is our agenda. We are going to follow these steps, which are first topic about the memory, then different structures of the data in the array, and then string workflows. So, first of all storing information process starts from, of course, memory. The fundamental and high-level question here, we could say that how is any type of the information actually stored in the memory? When we give these data computer, like let's say in the array, different types of the characters, like for example letter version like A, and then numerical version, let's say the 65, and let's say the Boolean data structure format like this, different types of the data. There is no actual data structure in its memory, I mean in our computers, because the memory can fundamentally store only like these numericals with 0 and 1. This numbers calls bits. If we represent these 0 and 1 bits, all of the possible combinations we could, let's measure. It will be like these formats. Let's say that 0 and 0, 0 and 1, and if we change their orders, 1 and 0, and lastly 1 and 1. When we count all of them, it will be 4 possible combinations, 1, 2, 3, and 4. Let's say when we wanted to represent, for instance, let's 0, 1, and it's 0 again, and we count all of the possible combinations, means the 8 possible combinations if we count them, and so on, other examples. So at the end of the day, we can prove the formula of the combinations, which is 2 power of n, based on that examples. When computer wants to store a certain amount of the data in the memory, that usually stores it as a group format. And this grouping is called bytes. And 1 byte is standardized as 8 bits. That means 1 byte can represent as 2 power of 8 is equals to, if you calculate them as mathematically, 256 different types of the possible combinations. All in all, 1 byte is 1 addressable memory unit. So, suppose we have a number, integer, let's say the 42 as an input, and we want to store it as 32 bits in the memory. So, the question why is especially 32 bit? Answer is because of grouping, and memory stores it basically 2 over 32 range of the numbers. And from input data to the memory byte pipeline is, firstly, we need to represent binary numbers, and then bytes, and then to the bits we can see the storing display. When we see in the some exercises, like from, let's see in our the exercises, let's say the -1 from to 0 or 1 to 2 over 30, 2 power of the 2 minus 1, this input size or input range, this is also sign of the 32-bit range for the memory. No, it is its total number of the combinations also became, if we calculate them to power of 32, is equals to approximately, if I'm not wrong, 4 billion possibilities. And when we expand the range to, let's say, the 64 bit, its combination also expand, and so on, like this. No, so all in all, it depends on the case or information that you wanted to store, of course. So if you finish up that example, which is 42, we need to firstly represent it as the form of the sum of numbers to power of 2. Like let's say 42 is equals to 2 power of 5 plus 2 power of 3 and 2 power of 1. So if you calculate them, it becomes their sum is equal to 42. And we divide them as a power of 2s, let's say 2 power of 0, 1, 2, 3, 4 and 5, because the maximum range is also 5. If it was intended, we can write down 1 or otherwise 0. 2 power of 0, yes or not? No, it didn't do that. 1, yes. Sorry, we need to write down 0 instead of 1. 1 and 0, 1, 0 and 1. If we represent it binary format, 10, 10, and again 10, yeah. And then final memory will store like this version. Let's say 32-bit means so the 2 slots fill it with the zeros. Let's see, 1, 2, 3, 4, 8 zeros one side, again 8 zeros one side, again 8 zeros 4 times, no? All of the total slots will be 32. All of these are zeros first of all. And each of these 4 parts are, let's say, the bytes, because of 1 byte is equals to 8 bits. That's why. 1 byte, another bytes. Input number is 42. And then we can store that our binary integer from the 42 from here, like 10, 10, and again 10. 6 bits. And additionally 2 bits we have as well. The question might become for that case, which is we are storing the 6-bit number in the 32-bit total slots. Is it non-memory musty? The answer is no. We wouldn't say that, because the main reason is memory stores any kind of input data as that bits and contiguous order. No? That means if you want to store them as 32 bits, that means any 1 unit or 1 million units of that number store 32-bit slots. It depends on the range as well. The reason is when we give the list of the numbers of any kind of information, let's suppose we have another types of examples which are not only for 32, then 100 plus and 7. These numbers we want to store. While converting them to the bits, memory need to filter the starting and when in which slot 42 is started and finished. And the same question for the 100 and other types of the numbers as well. And based on that structure, even though millions of the information represents in billions of the bits, memory can easily find their exact address with that formula. Let's say we have these addresses. Based on that case, we can prove the formula of the address, which is equals to base address plus index and multiply by element size. We can say, we can write down. Yeah. Let's see proof of the address formula with that examples with 32-bit memory. We can see 42 shows like 4 byte memory slot. Each of the bit consists 8 bytes. Total of this byte is equals to 32 bits. And for 100 also the same. And suppose addresses starts from 1000 and 1001 and 1002, etc, etc. And 42's belongs to, let's say, the 1000 to 1004 or 1003, let's say. And 100, this number belongs to 100 from 104 to, let's say, 107, and etc with other numbers as well. So the next number also represents the same, and final memory display them as horizontally after, let's say, each 4 bytes. Like 42 numbers territory is from 1000 to 1003, as I said. And the next input, which is, let's say, hundreds, this number's territory is from 1004 to 1007, and etc with other numbers as well. And suppose when we want to observe 42, we can use the address formula which we write down above, base address which is equals to, let's say, 1000 plus for 42 and plus index, which is, let's say, the index is located in the 0 because it's located in the beginning of the array, that number, sorry. And element sizes, which is 4. Why? Because of the standard size, it is standardized, it is integer 32, and address becomes, let's say, the 1000. That exact address we can store and we can get from the memory. And this condition is also because of these numbers, these elements are stored in the contiguous and depends on the programming language, of course. For instance, we are using C types of the language condition for that case. If you want to determine them, let's say the Python, it would be a little bit different because there is no any kind of the array, the structure in the Python. Instead of that array, it has a list as an alternative. We know the difference between the array and the list, of course. Array stores only the same type of the data, and while the list stores different types of the data, like as I said, a or true or any other types of the data as well. This is the main difference between them. So representing numbers, one more different thing we have, of course, about numbers representing in the memory, which is, suppose we are given input as a float format. Let's suppose we have not 42, 42.5. First, what should we do to store them in the memory? Firstly, we need to split it integer and plus like fractional parts. Let's say the 42 is integer part and 0.5 is fractional part. Then we can convert integer part, firstly binary of course, easily, and then about the fractional part to the binary, as I wrote 10, 10 and 10 bits. And to convert this 0.5 fractional part to the binary, we need to display as integer format for that case as well. Then it becomes, let's say, the 0.5 multiplied by 2, the integer. Why? To display as integer format. Then it becomes, let's say, 1 or 1.0 as in float format. And to represent it bit format, instead of that integer part, which is 1, we need to take the 0 as a fraction, and it would become, let's end of the data, sum the binary is 0.1, and then we can sum them. It's 10, 10, 10.1. It also depends types of the specific format and representation rule as well. This is a real storing in the memory as a float format as well. Okay, so quick question. Numerical store of the memory is okay. How about the character formats, like the letters? So answer is, suppose we have characters input as, let's say, the A, one word, one letter. Once again, the computer cannot figure out any information on its own beyond the basic bit representation, as I say. So we have to convert them numbers firstly, like the binary format, then it bit, and then we can store on the memory. For that process, we have standardized concept, which is called ASCII. A-C-A-S-C-I-I. It stands for American Standard Code Information Exchange. It is 7-bit encoding standard code. 7-bit encoding means 7 power of 2, which is equals to, approximately, if I'm not wrong, 128 possible characters or possible range information, let's say. So that computer can understand based on that encode. It looks like a manipulation, the multiplication table, we would say, that every character already displayed as a numerical format. One important is that ASCII also has a table of the English letter alphabets. Means its character length is, of course, limited. As I said, this is its limit. And to convert, if we have other types of the alphabet letters, we need another encoders. We will see them later, of course. So back to the word A, we have input like this. Let's imagine it's actually displayed on the ASCII's table. Its number is 65. If you check on the table, so when we convert it binary format, it becomes, and memory stores. If we convert it to the binary format, it becomes 01 and something 0 and again 01. That's understandable. Then we can store as a bit and etc. So storing these types of the alphabets in the memory, standardized again from ASCII, this encoder standard method. Another question, how about other types of the characters like the Kyrill or Chinese alphabets or emojis or other types of the data like the media files as well? So answer is, to store that types of the characters like the other data types, we can just use Unicode encoder. It gives Unicode point for every character. Let's say we want to store like this emoji, for example. This type of emoji converts like U plus 1F 600 or other types of the Kyrills like the Privyet in the Russian word This is the difference between the English word as well. This also, let's say, the stores these types of the encoders, Unicode. We don't have to memorize them. So that means U is actually the Unicode, standard Unicode prefix, and it represents as a hexadecimal display for easy recognizing, because other types of the data is also stored in with Unicode. It depends on which types of the encoding needable. These transformation of the Unicode formats are called UTF in the languages, in the tech words, we will say. It depends on which type of encoding needable, as I said. So it stands for UTF is Unicode Transformation Format, yes. And it has also some types of the different types like UTF-8, as we said, integer 32 or integer 64 or float 32 and etc. So it depends on how many slots given in the memory. Yes. It can convert another alphabet's words as well. So at the end of the day, we can see the mental model of the alphabets. We can see the process looks like this. We have input as an integer, the words or other types of the character alphabets, and then it converts Unicode character, and then Unicode points to encode them, and then decode them to the byte format, and then bits, and then RAM or memory, would say. So let's say, as an example, based on the Unicode table, we have the words like hello. Firstly, it converts Unicode characters. Let's count them. 1, 2, 3, 4, 5 characters we have. 5 letters or words. Unicode points represents each of the values or each of the letters to the Unicode format. Let's say U plus 54 and etc. E means U plus 0045 or 65 and etc. These types of the representation. And then memory is given an address and converts or decode them as bytes. And let's say the 5 characters becomes, let's say, the 5 bytes. And then we can easily multiply by 8, because 1 byte is equals to 8 bits. Then it becomes, let's say, 8 bits stores in the memory, that word. Another example is also text plus space and plus emoji. Let's say the hello, and then 1 blank space and emoji we have. How it actually stores in the memory. Again, the same formula, the same pipeline. Between letter 0 and smile sticker, that there's a space, as we say. It's also Unicode character actually, and it's taken into account as well. And the calculation also will be the same. This is the main difference. And when we have the mixed format, let's say the hello, and then space and world, and then space, let's say the privet in the Russian alphabetical word, and then space again, and then let's say the emoji, it also calculates and counts the same pipeline. Let's say the hello is 5 bytes, space is 1, privet, this word is, let's say, the 12 bytes after the converting them as encoding. And again, space is 2 bytes, and then let's say the emoji is 4 bytes. All of this calculating, summing them, and converting these bits, and then representing, storing in the memory. And when we storing the photos, let's say video or audio information, it divides them into the pixels firstly for the photo in terms of the photos. So images pipeline is, let's say that we have a real image as an input, and then it converts pixels and then compress them like JPEG format. It depends on the format as well. Let's suppose we have the RGB, which is a red, green, blue formats. It splits them as a pixels. Let's say the 1 pixel, let's say 01 is 1 RGB, pixel 2 is another RGB. If we have an 8-bit RGB, it's divided by them. Let's see, the R is 1 byte, G is, let's say, the 1 byte, or the B is also 1 byte, let's suppose, and it can be calculate them. And then let's suppose before encoding image size might be, let's say, the 3 gigabyte, and then after encoding it might be 3 megabytes. suppose when it's storing in the memory with them. So to recap the memory, if we are given input data asked how to store that in the memory, we can ask the following the universal clarification questions for any data structure. Here it is, we can clarify this mainly 5 questions. First of all, what is the logical data basically? Like, is it integer format or float format or boolean and etc. And the second question is, what representation we are using? Like, is it, if it is integer, what types of integer 32 or integer, let's say that 64 and etc. And the third one is, if it is relevant, what encoding we are using. Like, we are using ASCII or UTF, let's say the UTF-8 or UTF-16 or etc. kind of representation or encoding type. And then we could ask what bytes does it reproduce. Like, is it like the numerical, as we are given as 42 is integer 32 is conceptually 4 bytes likely, and these types of the questions we could ask. And lastly, how are those bytes laid out in the memory? Like, let's say we are using C types of the languages, it stores as a contiguous. Contiguous means, let's say that suppose started indexes from 1000 and then 1004 and then 1008 and etc. Each time it's increasing plus 4. Or other types of the languages might be contiguous or metadata format. Like, these clarifications are needable for storing the memory. So now we can say storing the elements contiguously in the fixed size sequence in the main mental model of the arrays, of course. We have tried to understood about the memory, and now we can move to the array data structure, of course. So to explain about array in one sentence, it is a data structure that stores elements as an ordered sequence. We can see in here the C-style fundamental arrays structure pipeline. We have, let's say, the same type plus fixed size elements, and then plus contiguous memory, and then index-based access. That structure is main pipeline of that array, we can see. For instance, we have integer 32 bits, and we have a numbers, let's say the 4 elements it consists, which is 4 element slots. Let's say we have it 10, 20, 30, and 40. Suppose each integer 32 measures 4 bytes each of the elements, and based on the base addresses also starts from 1000, as we also talked before. So 1000 belongs to the 10, and 1004, let's say after each of this element increasing by 4, it also belongs, let's say the 20, 1008, 1012, belongs 40, belongs 30. Each of these consists 4 bytes. They store in the memory like displays, so we based on that aspects we can find their address based on that formula, as we saw. Address is equals to base plus index and multiplied by element size. This is basically a representation of the array. So there are 2 types of the arrays, which are static and dynamic array. Static array is represents after the initializing new array, its length gonna be fixed. It's non-changeable. It cannot extend itself. That is why it's also static, as its name suggests. For example, let's say we have the integer 4 elements, as we say, and 4 means its capacity. That means it allocates only 4 byte memory, 1, 2, 3, and 4 square brackets. And when we want to append some elements, like based on the last samples, like we have the 40, which are the 4 elements, we want to add 1 square bracket, and 50 we cannot add, because there is no an extra array bracket for that element. Dynamic array is the opposite. It can extend, it allocates larger block, like one more 4 slots, let's say. We have already 10, 20, 30 and 40, and if we want to add the extra elements, we can add 4 more slots like this. And this process is called resizing. Based on that total slots, we have 2 main keywords in here, which are length of the array, which are how many elements are filled in the array, and we have a second one is capacity, which is how many total reserved slots in here. Let's say we have in the 8 slots based on all of the array's elements, we can say. So quick question in here, we added 4 more slots. That means 2x we expanded it. Why we especially resizing this as a double-sided? The answer is it is actually non-written standard. It's up to us as well. Suppose when we want to resize the array and we want to increase it plus 1 slot, let's suppose not as a double 2x each time, then copying the resizing the needable at each operation. We need to copy and we need to resize the element. That means this process worsens for the time complexity. And we want to increase not double as a triple. If you want to increase as 3x at each time, it might be better solution. But however, when we analyze time and space trade-off, it can be waste of the space because the resized array capacity cannot remove it again. That's why. So there are 3 main operations in array, which are read, write and remove. Let's talk about firstly read and remove. It's more understandable. So these operations can pick the element for read or delete them as their names. Their time complexity is, we can say, amortized O of 1. As we know, O of 1 is the best complexity and means that mostly works O of 1, amortized means, especially when we want to pick from the beginning of the array that elements or from end of the element, we can pick up. That's why it works much more better. And we can say the O of n. But why? Which cases belongs to the amortized? So amortized means mostly works of 1, especially when we're picking, as I said, the beginning or the end of the elements. However, in some cases it can works up to O of n. Why? Like here, let's say we have the 1 millions of the elements in our array and we want to pick or read or delete middle point of the slot. Let's say middle point is 500,000, that means. And it means we need to maybe pick or read 500,000 operations. That is why it's called amortized. So we also discussed about that in the last lesson, which was about the complexity topic, of course. So the next one is write operation. To understand this operation, we need to clarify 2 main cases, which are, firstly, if you want to write some element in the slot of our array, firstly, are there elements in array are there any elements in the array or it's null or fill it with elements? And the second question is to clarify them which part of the array we are writing, at the beginning or ending or middle part, which part? So if you're writing at the beginning of the array, even if the array is empty or filled of the elements, time complexity becomes O of 1. It's not actually filled, only empty element we can write, and its time complexity becomes O of 1. Because we're writing elements into empty array, that's why. And if we are writing in the end of the array, plus if there is filled with elements, its time complexity becomes O of n. because index, let's say if you want to add the filter element at the beginning of the part, let's say we have this number and you want to add, already have that in other numbers. That means we need to reposition all of the elements from another. That means we need to give the empty space for that slot for that additional element. That's why it can be work for of n time complexity. So these were basic concepts about arrays. So we can define about the next data structure, which is string. So string, as its name, it represents sequence of letter characters. String is generated by encoding in the memory as a sequence. For example, we have input like we saw before, hello. If we represent it as a separate sequence as characters, let's say the H separate, E, L, double L, and O, after encoding them, suppose we have, let's say, the UTF-8, we want to encode them, might become 68, 65, 6C, and it's like this format at the end of the day. It also depends on the encoding types, like it's interchanges like ASCII or Unicode as well. We talked before, like universal qualification questions. Basically, its pipeline is representation in the memory is the same as other data structures would say. And there are two main types of the strings, which are mutable and immutable. So immutable looks like a static fixed array, which is unchangeable. Once create new string, it doesn't change. Means it doesn't have it doesn't have any remove or update operations. That means, for instance, we have again input like the hello, and we want to change it first letter. Let's say want to remove, or we want to do the change to capital letter like this. What will happen on the backside? Firstly, it recreates new hello, these types of as an output and give the output, but the last hello, the last version of the word goes to the garbage collection. This is a main case of the immutable strings. And mutable string is a changeable. Once created, we can change and memory override it. We will see briefly on the operations we have. So there are three main operations, which are firstly read and slice. A little bit different name is concatenation. So about read, let's suppose we have, as we said, this word, and we want to get this as equals to with this variable, and we want to get as second index. That address, we can pick it, and its time complexity becomes all 1 easily. 0, 1, 2, 0, 1, 2. It becomes, let's say, the L letter. That's why its complexity is of 1. And about slice, it is also looks like a read, but it gets with a range. Like let's say we have as from 1 to third element. That means we need to pick the 0, 1, 2, 0, 1, 2, 3. E, L, double L. Basically, it creates a new string and then define the range. That's why its complexity becomes of k. K means this range difference. And the last operation is concatenation. It is actually adding strings, or we can say writing. This is also almost the same. Suppose we have these two variables and these strings. We want to concatenate, and means adding them. It creates new string firstly, and then move first and then the second one. That is why its time complexity becomes O of S plus T, let's say, or M plus N, etc. Depends on the variables and depends on that elements. So last but not least, about the strings, there is no any kind of the remove operation in the string, because there is no any kind of the in replace it. Suppose we have that text and we want to delete, let's say, any kind of the words. What will happen? The operation will come as usually expected, like this. But in the backside, last version goes to the garbage collection and create new version. That's why its time complexity also becomes O of n. So theory part is finished. We can solve the real practical exercises based on our topic. First, we can see exercise which name is valid anagram. So what we are given? We are given in the two strings which are s and t. We need to return true when t is anagram of the cs and false otherwise. Example 1, it gives input as in these words anagram and t is like this NAGAARM. Output is true. Why? Because all of the words also the same in the second variable as well. An anagram is also the string that contains the exact same character, which just as another string. But the order of the characters can be different. That's why, like this, we have an, the first value also we have an N, G, R, A, and with other orders also, words also the same. An example 2 refers in here, S is equals to rat, T is equals to car, and output is a false. That's why. So before solving that the task, first of all, we need to, as usual, clarify the task that we can ask. Let's say, firstly, should we assume strings contains only lowercase as English letter or arbitrary Unicode characters? They might be asked, let's say, to assume lowercase in English, let's like the A to Z, and fix it 26 alphabetical size. And the second clarification question might be, is character case significant? For instance, we have capital letter A differ from lowercase of A, and answer might be assume yes. And the third question can be, can string be empty? Like let's say S is equals to A and space B and space C, and T is equals to A, B, C without any space. The answer becomes yes, of course. They can be empty. So now analyzing part. Our boundary is clear. When we have the T is equals to 2 characters, let's see, or 3 characters, the second part of the variables, the length needs to be also 3 characters. There needs to be the same, and then they could be anagram. Otherwise, they aren't. Solution. First, one of the simple and the faster solution as its usual, which is brute force approach. Suppose we are given S to ABC and T to BAC. Basically, they are anagrams because A, B, B, and C, C. How we can solve them? Basically, we can solve first the simple solution. We need to clarify, we need to check that scan all of them for each element. We need to check firstly the A with B, A with A with C, and then separately the B with B, B with A, and with C, and C again with these steps. First loop becomes, let's say we have A of 0's element equals to A, B's 0 element is, let's say that first we are picking S 0 element, which is A, 2, T is, let's say, 0's element, then 1, then 2. We could stop when they will be the same. T0 is B. Is it the same or not? No, we can continue. The second one is A. Yes, we can stop in here. And the second loop we can see we have, and we can collect the results. Let's say visit counts. All of this firstly will be false. Why especially 3 false? Because we have the 3 characters. And then if once we found that element would be the turn is true. Then we can check the S first, the element index which is 1 is B. Then we are checking the separately again. Once we reach that element becomes that the same, then we turn it from false to the true. And if we count them, all of the operations, that becomes the first loop in 2 operations. Then the second one is, let's say, the 3 operations, and the last one is, let's say, this again 2 operations, and we sum them, 3 plus 2 plus 2, and becomes 7. And at the beginning of the condition, we have the 3 characters. Input is, let's say, the 3 characters. Output becomes the 7 operations, or it's almost the 9 operations we want to count. It becomes 3 of the squares of the 3. It becomes 3 of the square, almost. That means its time complexity becomes O of n square. And if we want to analyze its space complexity, there's only one additional new data structure, and we don't have create any new data types of the data structure. That's why it becomes O of n. So based on this analysis, time complexity is very high. Moreover, if there is a case like s equals to double a, like this case might be happen, and t is equals to also the a and b, suppose there are 2 letters on the first side and 1 on the other side as well, the second side variable. We can rescan it too. This is also a problematic case. So we can think about better solution. Let's say with sorting, we have B, A, C. After we sort them, A, B, C, the first side. And the second side also we can sort them. But actually we can see we want to follow up the working with the sorting solution, we can see that time complexity also gonna be high, because it needs to sort all of the characters, then it scan them all other elements. And in addition, sorting is also unnecessary task, because task doesn't require sorting letters. It is only asked determining whether they are equally represented on both sides or not. And basically counting firstly, and then just comparing frequency counts of both sides is more better solution for us. We can see with these examples as the given parts example, which are first variable is equals to anagram, and second variable is n, a, g, r, and m. So basically we just need to count of the first variable and check their second count of the elements of the second variable, and we need to count their frequency. Let's say how many characters we have in the S. 1, 2, 3, A we have. A count is 3, N's count is 1, G's count is 1, R's the same, and M's also the same. And T's case, N is 1, A is again 3, and others, G, R, and M also consisted, and frequency counts are the same. And then we can say their maps is equals to all of these are true. That means we can use with hash map, which is saves with k and value, and we can count them with the separate data structures for the frequencies. Suppose we have the first iteration, which is for the A's case, which is from first element of our first variable. We have 1 A's attended only once, and then we can check the second iteration as n, which is n is also we don't have in our count hash map. That's why we can write down in A is 1 time and n is also once. And the third iteration also we have again A, let's say, based on these words, A is attended once, and plus 1 it becomes 2. Increment we can do, and n again 1, and at the end of the day final result becomes A is consistent 3 times and others once, 1, and m also 1. And then first part is finished, that means the S first variable, and We can see the formula, which is count s and count t needs to be equal. When we convert it or move it from the s side, then our formula becomes count s minus count t. Their difference needs to become 0. We have already counts s, and we need to calculate separately counts t. That means we already have counts as hash map. First, we calculated the hash map of the s, and while we are calculating the hash map of the t, that means the frequency counts of the t, then we can just discrement them. We can decrease each of these elements. Let's say we have this is a count of s, and count of t, let's say we have again the same values. Could say all of the comparisons will be the 0, a of 3, n with 1, g and other variables also 1s. If our last comparison becomes 0, that means our result also true, which is this is an anagram. Otherwise, if there's one difference between them, we can return false. It's not anagram. They are not anagram. And if you want to calculate and analyze their time complexity, we don't have any extra for like inner loops. That's why we can write down in here their time complexity is equals to of n, and their space complexity only we have only one additional hash map, which is a new data structure. That's why its time complexity becomes of n. It's more better than of n square or of n logarithmic and other complexities as well. And based on this mathematical mental analyze, we can just easily convert it with code format, which are we have a function and we have two types of the variables, and answer needs to becomes Boolean types of the format. We can firstly write down the condition, which is if length of the s doesn't come equal of the length of t, we need to return false, of course. They are not anagrams, that means. And to collect case and values, we need to write the new hash map. We need to write down count as its name, and we can write firstly the counting for the characters in s, which is the first our variable, and we can write down the condition, which is if characters in the count, which is the case value consistent hash map. Then we can write down count of the character. We can write down plus and equals to 1, the summing them or incrementing them. Otherwise, we can just keep them, characters equals to 1. So first variable part is finished, and then we can remove the t characters, which is for again character in the t. If the character is not in the count, we can just return false immediately. And then we can just write down character of the count minus n equals to that, decreasing them as 1. And finally, we can check all of the frequencies, which is for value in count dot all values. If any value becomes 0, we can immediately return false, of course. Other case, yes, we can return true, which is these are anagrams. If we can check the codes. Oh, wrong answer. I think because of we wrote in the discrement inside the if condition, we need to write the else condition. We need to recheck again, and we can see all of the cases are worked. So to recap the topic, these were about the memory, array and strings, how they are worked actually.